bits. Okay, so an attacker would have to do 2 to the 128 operations, which is a trillion times harder than 2 to the 80 about. Okay, or even more, 256 trillion. Okay, so that's S. The next part is P. P is the size of a public key. So how do we determine the size of a public key? Well, it depends on two things. One, it depends on the security level you want. Do you want 80-bit security or do you want 128-bit security? Now, if you want 80-bit security, you can't use an 80-bit public key. Reasons, if you've studied cryptography, you probably understand. So for 80-bit security, you might use a 1000-bit public key if you're using RSA or something like that. The other aspect of the choice of P is exactly what public key system you're using. If you're using something like RSA or Elgamal or Diffie-Hellman, your keys are this big. If you're using something like elliptic curves, your keys are much smaller for the same security. Okay? So that's a benefit of using something like elliptic curves. So I'll give you a couple different parameter selections so you can see how the systems compare. So first, I'll use the kind of traditional numbers mod n, right? Zn star kind of system. So we're talking about RSA, or we're talking about Elgamal or Diffie-Hellman in numbers mod some other big number. So here I've chosen R equals 5, S equals 16, again 16 bytes is 128 bits, so we're talking about the stronger level of security here. I'm talking about P equals 256. Okay, 256 bytes is 2048 bits, and we're going to say that a 2048-bit public key is about the same strength as a 128-bit private key. Now it turns out that's not true. A 128-bit private key is more like a 3000-bit public key, but we're underplaying it here because underplaying it gives an advantage to the other schemes and a disadvantage to ours. So we're being conservative here, okay? And you see, even with that conservative choice of parameter, we still, so Sphinx's overhead is now 448 bytes. It's still quite a bit smaller than any of the others except for Minx, which of course has broken security, so it doesn't really count, right? It's easy to design a really small overhead system that is insecure. Okay, we don't want to use that one. Okay, let's look at another choice of parameters. Here we're going to use elliptic curve cryptography. Again, we're going to use R equals 5 and S equals 16. And now the appropriate size of a public key is 32 bytes, okay, or 256 bits. And that's quite accurate for 128-bit symmetric key strength. Okay, and here you see Sphinx is smaller than all of the choices except for SSH-08, but SSH-08 has this problem of constructing messages being very expensive. Okay, so we're a little bit bigger than SSH-08, but we don't have this expensive construction problem. If we choose other sets of parameters, such as if we use 80-bit security and R equals 3, we can actually get the overhead of Sphinx down to exactly 100 bytes. And now it's not only comparable to the size of a tweet, it's smaller. So now you might imagine putting the mix header inside the tweet. So you could use Twitter as your communications mechanism for your mix system. And that's an interesting thing that I and my group will be exploring hopefully soon. Of course, the problem there is that your message size is now only 40 bytes. And that's a little small even for tweets, right? So more work needs to be done to see if we can squeeze even a few more bytes out of this header and get it a little bit smaller. But in any case, we're down to something in a reasonable size now. Even for this high security system where we have 224 bytes, that's comparable to the size of a tweet, 140 bytes. It's not like the kilobytes that we saw on the previous slide here, right? Okay, so what actually is the Sphinx message format that I've been talking so much about? Here's where the Greek letters show up. So a Sphinx message consists of 4 parts. The header is alpha, beta, and gamma, and the body or the payload is delta. Alpha is an element of a public key group G. And what is this group G? It's any group satisfying a particular assumption called decisional Diffie-Hellman. And this is just a kind of standard mathematical assumption that we make. It's one of these assumptions like factoring is hard. Okay? It's not that one, but it's a similar one that all of cryptography relies on certain problems being hard. And unfortunately, we don't know how to prove that those problems are hard for the most part, so we just make assumptions that we presume that it's not the case that everyone is insane and these problems really are hard. So this is the problem, decisional Diffie-Hellman. So what kinds of groups are we talking about? So in our implementation, which is written in Python, we have an implementation of a choice of group. You can either use ZP star for 2048-bit prime P, or you can use Dan Bernstein's elliptic curve implementation called curve 25519. A nice advantage of the latter is that, as we said before, when using elliptic curves, alpha can be just 32 bytes, okay, which is pretty short. And an important point is that there's only one alpha no matter how many hops there are. Okay? And we'll get back to that in a minute because that's a really important property of Sphinx. Okay, then beta, so that's alpha. Beta are the nested routing instructions. Okay, so it's the addresses written on the envelopes wrapped in the other envelopes wrapped in the other envelopes. Okay? And so it has both the identity of the next hop, the address of the next hop, and any of these parameters Alice might wish to communicate to the nodes as part of the mixing strategy. Okay, gamma is then a MAC of beta. MAC is a message authentication code. It's basically a secure cryptographic checksum to make sure that nothing has been modified in transit by an attacker. Okay, you probably know about MACs. And then delta is the multiply encrypted message payload. So it's the actual message encrypted, encrypted again, encrypted again, encrypted again, and each mix node will remove one layer of encryption. Okay? So how do we set up the system? We give each node a public-private key pair, and the way we do this is just the kind of standard way we do it for a system like El-Gamal. Every node picks a random secret key called X, or XN, for node N, and its public key is just G to the power of XN, where G is a generator of the group G, capital G, okay? And we call that YN. YN is G to the power of XN. So YN is the public key, and XN is the private key, okay? And then the way Alice shares some secret information, like the identity of the next hop, or these other mixing parameters, with any given mix node, is Alice picks her own random private key X. She computes alpha as G to the X, and computes the shared secret S as YN, the node's public key, to the power of X. Okay? And the node's public key YN is G to the XN. Let me point with the mouse here. So YN to the X is G to the XN to the X. Okay? Then the node N will receive alpha, can take alpha to the power of its private key XN, and get alpha to the XN, but alpha is G to the X, so that's G to the X to the XN, and you can see that G to the XN to the X equals G to the X to the XN, by just the properties of exponents. Okay? And now, so this is just the standard El-Gamal, Diffie-Hellman type thing going on. If you've studied cryptography, you'll have seen this before. And then S is a shared secret that can be used for whatever, symmetric key encryption, MACs, anything like that. Okay? So this is how Alice shares some secret information between her and any given mix node. Now, Alice has to share secret information with not just one mix node, but our mix nodes. Okay, 3, 5,